Today we're going to look at the vertex form of the equation that we've been looking at over the last couple of days, but we're going to look at it with a slightly different lens where we're transforming our parabolas. So it's what we were doing with Desmos the other day, and we were talking about how the certain parameters, the a, the h, and the k, really pick up the original parent graph of y equals x squared, and it just moves it or changes it in some way, shape, or form. So what I have written here, and you should make this a note for today, transformations of parabolas. The vertex form of the parabola, not only does it tell you your vertex and your direction of width of opening, it also describes the parabola as a transformation of the parent function. So the parent function y equals x squared, that is your most basic parabola. That's the simplest parabola that we can have. Every other parabola can be written as a transformation of that one. We can reflect it, we can stretch it or compress it, we can move it to the left or right, we can move it up or down. And every other parabola can be based on that one. That's really what the vertex form is talking about or doing. So we talked about the a value the other day, and that tells us our width and direction of opening. Specifically, we were focusing on just direction of opening. If your a is positive, so if a is positive, meaning it's greater than 0, we don't have any reflection at all in the y-axis, in the x-axis. It's not being flipped over. So we say there's no reflection. No reflection. And I'm really making a mess writing this down, so I think what I'll do is I'll put me on pause and clean this up. Okay, so if the a is positive, if it's greater than 0, then it's opening up and the original y equals x squared has not been reflected. But if a is negative, so what I have written here, let me see if I can find the right color highlighter. Doesn't really matter. If a is less than 0, that means a is negative. If a is negative, there is a reflection in the x-axis, and that's the thing that takes that parabola and turns it upside down. So that's what makes the opening be down, that reflection. Now the other thing we talked about is how that a value tells you whether you have a wide opening or a skinny opening. And any value of a that's between -1 and +1, not including 0, a can't be 0, or that gets rid of our x squared and we don't actually have a parabola anymore. But if your a value is between the -1 and +1, or close to 0, those ones are the wider ones. And what we say in terms of transformations is that we have a vertical compression by a factor of 1 over a. So I'm just going to write that in. And then if a is bigger than 1 or less than -1, like a -10 or a +10, that's a vertical stretch by a factor of a. And I'll try and do a little demonstration for you on that. But I can't do that on here. I have to do that in person. Okay, so again, if a is between -1 and +1, that's when we have it opening wider, and we say that our parabola has been compressed so that it squashes it down and it's not as narrow of an opening as it was before. If a is bigger than 1 or if a is less than -1, we have a vertical stretch, and that makes it skinnier. We're stretching those y values up. Okay, the next piece that we need to look at is the h value, and we know that that is the x-coordinate of the vertex. So that we also know from the Desmos is an actual horizontal translation, h units to the left or to the right. So we're really picking the graph up and moving it left or right by changing that x-coordinate of the vertex. So I'll just write that in here, and then we'll talk about the k. All right, and then this k value here, that is the y-coordinate of the vertex. That really lifts that graph up or shifts it down, however many units k is. So that's what we call a vertical. So vertical goes up and down. That's a vertical translation. K units up or down. Okay, so we're going to actually put this into practice in a moment on our next slide. Okay, one thing that we need to make sure we make note of is that you have to apply vertical stretches and or compressions as well as any reflections before you do any translations up or down. Okay, so the up or down thing, the adding comes last, the multiplying, the vertical stretch. That's a multiplication, the a value multiplies, so it has to happen before we actually move the parabola up and down. So our example here is state the transformations, each of the transformations that have been applied to our base parabola of y equals x squared to obtain the graph of each of the following. Be sure to use the correct order. In other words, put those reflections and the stretches before we do our translations up or down. So this first one, looking at the a value, I have a reflection in the x-axis because it's negative. We have a vertical stretch by a factor of 2. That's going to make the parabola skinnier. The vertex, the x-coordinate of the vertex is at positive 9, so that graph's been picked up and moved 9 units to the right. And then we're moving it 3 units up because the y-coordinate of the vertex is now at positive 3. So I'm going to write all those things down, and I want you to make note of where each of those things is coming from. So this is the order in which I will apply all of our transformations here. All right, example B, I have y equals 1/4 x take away 2 all to the exponent of 2. In terms of my transformations, I have this 1/4, which I know my parabola is still opening up, so I don't have to worry about saying anything about a reflection. There's no reflection at all. But that 1/4 is pretty close to 0. That's going to give us a much wider opening parabola, and we call that a vertical compression by a factor of the 4. We're looking at the number on the bottom here. Vertical compression by a factor of 4. This piece tells us the x-coordinate of the vertex is 2. It's positive 2, so it's been moved 2 units to the right. And then you'll notice we don't have anything on the end of that. That's like adding 0. We don't have to worry about making any kind of vertical translation on this one. All right, so I'll write those 2 steps in, and then we have another example. Okay, for part C, I have y equals 3x squared minus 5. So my a value is the 3. There is no negative. I don't have a reflection. The 3 is the bigger than 1, so I know that that is a stretch. It's going to make my parabola skinnier. So a vertical stretch by a factor of 3. I'm subtracting nothing from x before I square it, so there's no horizontal translation left or right. And then I have this extra minus 5 on the end. That is your vertical translation, down 5 units. So we will write that in. Now, in terms of what all of this means, is that I could start with any graph of any particular, I could start with the graph of just y equals x squared. So here's my x-axis, my y-axis. And let's say I'm doing part A. So my original y equals x squared looks something like this as a parabola. That's just our y equals x squared. If I were to reflect it in the x-axis, so my first step, reflect it in the x-axis, it's going to take that parabola and create like a mirror image over the x-axis. That's what reflect in the x-axis means. And then I'm going to stretch it by a factor of 2. So what that means is it makes it skinnier. So in red, this would be my parabola stretched by a factor of 2. Really, I'm just taking all these y values, and they should be twice as far from the x-axis if I do that kind of correctly. I might be out just a little bit there. Let me try that again. So my distance from the x-axis is this much, so when I multiply it by 2, it's twice as far. Distance from the x-axis at this point is this much. I need to double that. It's going to be here. So in terms of my parabola is going to have a skinnier opening when I stretch it by a factor of 2. I'm really multiplying on my y-coordinates by 2 here. Then I'm horizontally translating that 9 units to the right. So now I'm going to use yellow here. I've got to pick up the red graph and move it, sorry, this is green, not yellow, and move it 9 units to the right. So my vertex now is over at 9, 0. And it's still skinny, it's still opening down. So it's still skinnier than my y equals x squared, still opening down. So that's the 9 units to the right, and now I need to translate that 3 units up. Now I'm going to use yellow. So my vertex, which is at 9, 0, is now going to move up 3. 1, 2, 3, pretend it's there. Open a relatively skinny. So just slide the whole thing up. The new vertex now is at that 9, 3. Okay, so that's really how the transformations are working in terms of the graph. Now I'm going to take you one more slide to show you one more thing. Okay, what I've created here is the table of values, just a partial table of values for y equals x squared, so my parent function. And I'm just going to show you how all of these pieces, that reflection, that stretch, the moving to the right and moving up, affects all of these points. If I were to take my coordinates that I have here, and if I were to take them and reflect them over the x-axis, what that does is all of these y coordinates here become negative. So if I reflect over the x-axis, my new table of values looks like this. My x coordinates don't change. They stay as they were. My y coordinates all become negative. I'm just really multiplying the y coordinate by -1. And in fact, if I were efficient with this, I could at the same time then apply the vertical stretch. So this is taking my y values and all of them are going to be multiplied by 2. I'm going to stretch by a factor of 2. All the y values get 2 times, stretch by 2 times as big as they were. So my x's don't change. My x coordinates stay the same, -1, 0, 1, 2, and 3, but my y coordinates are now going to double. I'm timesing y, multiply y. Yeah, that looks like xy, but multiply, that's the operation, multiply y by 2. So -4 times 2 would be -8. -1 times 2 is -2. 0 times 2 is 0. This will be -2. This would be, double that would be -8. Double the -9, that becomes -18. So those are my new ordered pairs. If I was only doing a reflection and a stretch, my original parent parabola would end up having this set of ordered pairs. But from here, I'm going to take that now, and I'm going to move everything right 9 units. Now, if I'm moving everything to the right by 9 units, right, 9 units, my y coordinates don't change. It's my x coordinates that are going to change because everything's just sliding left or right. It doesn't affect the values of the y, it's only the x. So I'm really going to add 9 to x to get there. So -2, add 9, should be +7. -1, so really, in case you're wondering where I'm at, I'm really taking these x coordinates here and I'm adding 9 to every single one of them. All right, so if I was at -1 and I add 9, I should be now at 8. 0 add 9 takes me to 9. 1 add 9 is 10. So all of my x values in the original were just going up by 1. These are also now going up by 1. 7, 8, 9, 10, and then 11 and 12. All right, and my y coordinates stay the same when I move it left or right. I'm not switching anything up or down. And then -18. And then my last move is that I want to take my coordinates and move them up 5. So if we're moving up 5, I'm not moving left or right. The x is not going to change. We're moving up 5. We're going to add 5 to the y coordinates because everything has to slide up. So my final set of ordered pairs would have the 7, 8, 9, 10, 11, 12. 11 and 12. And all of these y coordinates have 5 added to them. So -8 add 5 would be -3. -2 add 5. Oh, lordy, lordy. -2 add 5 is +3. I'm getting very tired here. 0 plus 5 is 5. -2 add 5 is 3. And that should make sense because I have my symmetry happening here. So -8 add 5 would be -3. -18 add 5 would be -13. So that would be a set of ordered pairs that could help me graph it if the transformations are kind of tricky for you to see. This is just an alternate way of doing that.